Now, yesterday I spoke of equation with absorption term, with nonlinear absorption term. Now we like to speak of equation with a reaction which is a source. Okay, and you see, I have two model equations which go back to the 19th century actually, the Lane-Emden equation and the Emden equation. Okay, they were studied. The first study probably was due to Emden in 1897. And for Emden, assume that lambda is positive. Now, concerning the Lane-Emden equation, I have explicit solution. Always the idea is to first to look for explicit solution if I want to study singularities. Okay, if I want to look for equation like u of r is a times r to the b, this implies again that b is -2 over q minus 1. As for the coefficient a, it exists if and only if q is bigger than n over n minus 2. And it has the explicit value a is minus lambda n q to the 1 over q minus 1. Remember that we have already used lambda n q for equation with absorption. So this is the opposite. So this is the opposite. Okay. So this is only in that case that we have solution with explicit solution. Now for Emden equation, we have explicit radial solution, which in those form, u of r is 2 logarithm of 1 over r plus logarithm of 2n minus 2 over lambda. Okay. Now, if consider equation which are of the type minus Laplacian of u equal a positive things, then there is a key observation which is called Brésis-Lyon's lemma. And it says the following, that if you take a function u which is in L1 of BR, such that the Laplacian of u is in L1 log of BR minus 0, the Laplacian being taken in the sense of distribution, and assume that we have for some function f in L1, and from some coefficient a positive, you have that Laplacian of u of x is less or equal to a times u of x plus f of x almost everywhere. Then this implies that u is in L1 log of BR, and there exists a coefficient alpha and a function phi in L1 log of BR, such that minus Laplacian of u is a of u plus phi plus constant. Okay, so this is some explicit constant depending on n times alpha to the delta 0. And after you have this, because u is in L1 and phi is in L1, then this is an observation that the limit when x goes to 0 of the average of u on the spherical on the sphere y equal x divided by mu2 of x, this is equal to alpha. Okay. This result actually is not very surprising. Some people working in harmonic analysis, and it's probably when I discuss with people in working with that, and they say that this is more or less classical because it is a superharmonic for positive superharmonic function. Okay, this is in this sense that also for a positive superharmonic function in a smooth domain, then you have a trace on the boundary, which is a bounded Radon measure. This is called Doob theorem. Now, as a consequence, if we look both for Emden equation and for Lane-Emden equation and for Emden equation, we know immediately the following, that UQ for Lane-Emden, UQ is in L1. For Emden, exponential of U is in L1, and their holes for the first equation minus Laplacian of U equal UQ plus Cn times alpha delta 0. And for the second equation, minus delta of U is lambda exponential of U plus Cn plus alpha delta 0. Now, actually, this is not really informative because alpha, for example, for equation for Hemden equation, alpha is always 0, and for Lane-Hemden equation, alpha is 0 when Q is bigger or equal to n over n minus 2. Okay, so it is not really an information. It doesn't give anything about the behavior. That means, okay, I will say in some sense that for this type of equation, the singularity is not detectable in the sense of distribution. Okay, also something which is interesting that for both equations, by the maximum principle, any non-negative solution of equation 3.8 is bounded from below by the solution minus delta G equals Cn alpha delta 0 with Van Nistelrooy boundary. Okay, so we have an estimate from below. Now, if we go now to Lane-Hemden equation, the first interesting and important result is due to Lyons, Pierre-Louis Lyons. It appears in 1980 and essentially proves the following, that for n bigger or equal to 2, for Q between 1 and n over n minus 2, if you take a non-negative solution, which is C2 of BR minus the origin, assume that it is a solution in BR minus the origin, and in that case, there exists some alpha, such that we have alpha is positive or 0, such that we have the previous estimate here, this one, okay? And furthermore, which is much more interesting, that u of x is between alpha times mu2 of absolute value of x minus mu2 of r. So this is a green function. This is the solution of this equation with Van Nistelrooy boundary, and is bounded from above by a alpha times mu2 of norm of x plus some constants. Okay, and if alpha is 0, u is smooth. So you see that in this sense, that when q is between 1 and n over n minus 2, u behaves like the green potential of the Dirac mass. Okay, and concerning now the equation, the Lane-Hemden equation, the Hemden equation, we prove with Richard that we have a similar result, at least in dimension 2. For the Hemden equation, the dimension is absolutely fundamental, you will see. So in dimension 2, it's very easy to, it's not very easy, but not difficult to prove that we have this type of estimate. If you take a solution of minus Laplacian of u equal exponential of u in puncture ball minus the origin in dimension 2, then we have this estimate. Alpha times log of r over capital X is less or equal to u of x, and is dominated by alpha times logarithm of r over norm of x plus some constants. And it is also that it's easy to obtain by with small constants alpha, that you can find existence of a non-negative solution of the equation. When alpha becomes too large, then the construction we have, those solutions become change signs. Okay, so this was called the subcritical case. Now, the supercritical case is a case where Q is bigger than n over n minus 2. And it's also this is for the Lane-Hemden, and with n bigger or equal to 3 for the Hemden. Now, such similar solution, we know that there exists a solution which are invariant by the transformation TL that I have already defined, which is TL of u applied to x is L to the 2q over minus 1 times u of Lx. Then we know that they have this form here. They are this form, and omega now satisfies this equation here. Minus delta prime of omega minus lambda nq omega minus uq omega q is on 0 for a positive solution. And this equation actually is a particular case of a larger class of equation, which is the following: minus delta g of omega plus lambda of omega minus omega q is 0. Remember that if we want to have something of interesting, minus lambda in q should be positive. Okay? If it is negative, you see immediately also that there is no solution, you just have to integrate. Okay, now I take a more general equation than this one. I replace the sphere by a n-dimensional compact complete Riemannian manifold. That means with no boundary. I assume that G is a metric tensor, delta G is a Laplace, and the Ricci tensor is, which is a trace of the full tensor, of the full Riemannian tensor. This is, I call it Ricci with G, okay? And now Gidas and Sprague first, they study the result concerning the existence of what is the main question? The main question is whether the solutions are constant or non-constant. Okay, the first starting result was due to Gidas and Sprague in their Communication and Pure Applied Math from 1981. Then we extended with Laurent Veron, we extended this in another paper in 10 years after in Invenciones. And finally, but both the paper of Gidas and Sprague and Laurent Veron and myself, they were dealing with solution where there is the Ricci is positive. Actually, with the Liqua, and we extended the result in 1995, and the extension is the following. So we assume that Mg is a complete Riemannian manifold, compact. Lambda is positive. I assume the following now. The Ricci, which is a two tensor, is bigger or equal to R times G. Okay? R is non-negative. And you assume now the Q minus 1 lambda, okay, is less or equal to the lambda 1G. What is lambda 1G? This is the first non-zero eigenvalue of the Laplace on the sphere. Since the manifold is compact and complete, 0 is the first eigenvalue always, and with eigenfunction, which are the constants. So now there is a first non-zero eigenvalue, which is lambda 1G. I assume that if I have this estimate, so Q minus 1 lambda is less or equal to lambda 1G, plus this complicated object, which is Q, the dimension is D, remember, Q dd minus 1 divided by Q plus dd plus 2 times the Ricci minus d minus 1 over d lambda 1G. Okay. I assume also that Q is between 1 and the critical exponent d plus 2 over d minus 2. Okay. And well, now among those two inequality, if the manifold is the sphere SD with a metric which is k times the standard metric. It's called that this metric is conformally equivalent to the one of the standard sphere. Then in that case, I have to assume that one of the two inequality here is strict. So what is the result? Any non-negative solution of this equation here is constant. It can be 0, or it can be lambda to the 1 over Q minus 1. Okay? And the technique of proof is based upon there is a strong inequality, which is due to Bochner and Weissenbach, and which essentially on a manifold says the following, that we have 1/2 of the Laplacian of grad psi square, is equal to the Hessian of psi to the square, the norm of the Hessian of psi to the square, times the gradient of delta G of psi times delta G of psi, plus the Ricci tensor here of psi psi, okay? Now, these terms, which could be a complicated one, but because of Cauchy-Schwarz inequality, we have the Hessian of psi to the square is bigger or equal to 1 over d times the Laplacian of psi to the square. So, in some sense, you can replace now all the terms which appears as Laplacian of psi and this term also, you replace by the equation here. So this is actually, this is the basis of the construction of the starting of, in some sense, it's a geometric starting of the Bernstein method. Okay, now I look at the example when n is bigger or equal to 3, and I assume that mg is a sphere Sn minus 1 G0, then the Ricci tensor is n minus 2 times G0, and lambda 1g is n minus 1. So for that, I have that any non-negative solution of my equation, of the starting equation, which is this one, here on the sphere, and it is constant if, immediately when q is less than is between 1 and n plus 1 over n minus 3. Okay? Now, and this result actually was obtained first by Gidas and Spruck when n is bigger or equal to 4. There is an interesting case, which is to notice the case. Remember that here I have not put the case q equal n plus 1 over n minus 3. Because in that case, we can use a stereographic projection from the Sn minus 1 minus the North Pole to the plane Rn minus 1, and it transforms exactly our equation into this minus the critical one equation, minus delta of omega tilde is omega tilde to the n plus 1 over n minus 3. And in that case, we know that the solution have there is a whole family of solutions which have this form. Okay, so they cannot be constant. So this is why it's excluded. Okay, something also which is noticeable, which is interesting, is a case where M is has a zero curvature, flat. It's called a Ricci flat. And the example is take for M the flat torus in Rd, which is 0 to the pi to the power d. And the solution are what? What means a solution on this, defined on this torus? That means it's a function of the x1 to xd, okay, which is 2 pi periodic in each of the variable. So in that case, r is 0, and it's immediate also that lambda 1g is 1. Okay, so you find exactly now the condition. If lambda 1g equal 1, in that case, you can find the condition under which a solution in the sphere in Rd, which is 2 pi periodic in all direction, x1 to xd, is necessarily constant. Okay. Now the second problem with equation with source, which is also you see that equation with source are much more difficult than equation with absorption. Okay. Existence of constant solution is a problem. Second problem again is obtention of a priori estimate. Now I'm going to increase a little the class of solution which I can consider. I am going to add a RD potential here and a power against the UQ. Okay, and Gidas and Spruck proved with the mu is 0, and we obtain with general mu the following result. You take any for n bigger or equal to 3, and q is between 1 and n plus 2 of n minus 2. Mu is in R, and sigma is in R. If you take a positive solution of this equation, it may not exist, of course, but a positive solution of this equation in B1 minus 0, then you have the expected estimate. U of x is bounded by c times x to the minus 2 plus sigma, okay, divided by q minus 1. This is on the ball B over 2. And the proof is extremely involved. It's not an easy one. First, you transform the equation by putting u is v to the minus b, beta. So you have a new equation here. Then again, you use Weizenburg formula, but now it is in Rn, so there is no Ricci tensor, it is 0. And you have this, and you replace now delta G, you replace it here, you have it here, you replace by this expression, okay? I think it should be grad of delta V, not here. Okay, it should be grad of delta V, okay? And you have a ugly object that you multiply again by eta times V to the gamma, where gamma is free, and eta is a cutoff function. And what happened? It's a bit complicated. It takes a lot of room. It can be computed with a computer-assisted proof, but at that time it didn't exist. And after that, you try to optimize. Remember, I have two free parameters, beta and gamma. You optimize those free parameters in order to have an estimate. Remember, if the key point for such estimate is to get usually to get an Harnack inequality on a sphere of radius x. And in order to have an Harnack inequality, according to what I have exposed about serine, it's important to estimate the coefficient of u, that means uq minus 1, in some LS space. Okay, and now what we did that we obtain these estimates, and with that we have the Harnack inequality. We have the Harnack inequality, which is really the key. Now, after we have Harnack inequality, you just essentially you try to look at the average of the function u, which is it, and the average of u on always this is average. Remember on x equal r. Okay. So I have this estimate. I make the average, and what you know because of Harnack, you know that the u bar to the q is less or equal to uq bar, that means the average of uq, and again is less or equal to kq, Sn, the norm, the measure of Sn minus 1 to u bar q. So in some sense, you have a very good balance on u bar, and you replace this by a differential inequality, and this differential inequality, you can integrate it. Now, what happened with that? Okay. Suppose that you are in the case where mu plus lambda nq is negative. Okay. You take a positive solution. So I go back again to this equation here. I go back to this equation here. I assume that you have a positive. I'm going to just give a very general result. I'm going to give a very general result, which is actually not directly dependent of what we proved before, but in some cases it is dependent because they are estimate. So you take any positive solution of my equation here, the equation with which is here. Any positive solution in the puncture ball. Okay, and you assume that I take sigma is 0 for simplicity here. I take sigma is 0 and assume that x to the 2 vacuum minus 1 u of x is bounded. Okay, we know that in many cases it is bounded, but remember that here I take Q any bigger Q bigger than 1, different from n plus 2 and minus 2. So in that case, we have the following alternative. Either there exists some k positive such that limit of u of x divided by mu2 of x equal k, or there exists a positive solution omega of I call it the stationary solution, this equation, minus delta prime of omega minus mu plus lambda nq of omega minus omega p is 0, such that limit x r to the 2 over q minus 1 u of r and dots is omega. So now this is a more general result. Remember that here I have no, this is an assumption, and we know that this is satisfied if q is less than n plus 2 and minus 2. Now I take a very general, I assume that I take any solution which satisfies the a priori estimate. And there is still this problem. We don't know what is the set of solutions, the set of positive solutions of this equation. If q is subcritical, we know that the solutions are constant, but or it should be omega to the q, I'm sorry, here. Should be omega to the q. So, but if q is supercritical, can be much more complicated. But the basic for proving this result, what we say? We said t is, again, we use the mn variable, t is minus logarithm of r, and I say that v of t and sigma is r to the 2 over q minus 1 u of r and sigma. So now I write my equation here. I write the equation in the cylinder, minus vtt plus theta times theta nq times vt, minus delta prime v, minus the same thing here. All this part is the stationary part, minus mu plus lambda nq v minus v to the q. So this is satisfied in t infinity cross Sn minus 1. Okay, now if q is if q is less than n over n minus 2, and we know that in that case, I'm sorry, I have to be careful, that in that case the set theta nq is different from 0, okay? And the set of non-negative solution of this equation here, of the equation, the stationary solution here, is reduced to 0 and omega 0. This is the result of what we have already proved. Now the energy method apply immediately, and it implies that V converge either to 0 or to omega 0, because the limit set is discrete and there is with only 2 elements. We can use directly the energy method. There is no difference. When Q is bigger than n over n minus 2, we need a new approach. This is a very powerful approach, which is based upon Simon's theory of analytic functional. He has published this in the Annals in 1983. And this is the starting point is a result from analytic geometry, which was published by Lojasiewicz in 1965. And what is a Lojasiewicz inequality? You take f, a function from Rn to R, which is an analytic function in neighborhood of a point A of Rn. Then there exists tau positive and theta between 0 and 1 over 2, such that the grade of f, the norm of grade of f, is bounded from below by f of x minus f of a to the 1 minus theta. So the proof is extremely complicated. This is purely algebraic geometry, analytic geometry more precisely. No, so this is the basis. So what did Simon? Simon made he extended to an infinite dimensional space. The idea of Simon was not at all to study the singularity of solution. He was studying the tangent cone to minimal surface. So it was completely different, his idea. But the technique is exactly now, the technique is called the Simon's technique, and it has been used. It works for parabolic equation, it works for hyperbolic equation, for also for elliptic equation in cylinder, in which you have this type of formalism with f being an analytic function. Now, the theorem of Simon says the following. You take f to be a real analytic function which is defined in some open interval I. Okay, you assume that A is different from 0, and V is a C2 solution in this here. A is fundamental that it is different from 0 because it is a damping term, so that we can start the energy function. Okay, you take a function of this equation here. Okay, and you assume that it is, I think, well, it's important that it is that V is bounded. We assume that V has value in a compact subset of I here. I is open, remember, so it's bounded and it has value in a compact subset. So on the set of value of V, the function f is analytic. So now there exists a function omega in C2 of Sn-1, which satisfies the stationary solution here, minus delta prime of omega minus f of omega is 0 in Sn-1, such that you have the limit of Vt of t in C2 plus the Vt, the norm of Vt minus omega in C2, this is 0. So that means that under this condition of analyticity, the trajectory choose a particular element of the set of stationary solution. Now, if we want to apply this result with minus mu plus lambda nqv minus v to the q, we first prove that we first need the following, that either v goes to 0 or there exists an epsilon positive such that v is separated from 0 here. Okay, and this is obtained, and if it is separated from 0, then the range of the value of v belongs to the range of analyticity of this function. Now, if we go to the equation, the Hemden equation, for the Hemden equation, well, we have first the result with Richard, and the most of the case is the case of dimension bigger or equal to 3. First observation, there is no a priori estimate. Furthermore, if n equals 3, it cannot exist any universal a priori estimate, in the sense that you have that u of r and sigma minus 2 logarithm of 1 of r sigma is universally bounded for r between 0 and half, for example. Okay, this is a very important observation. Now, so you are really in the case where the energy method cannot apply up to the end. We need, again, something new. So now what do? If you look at the equation like this form, you code u of r and sigma is minus 2 logarithm of r plus 2 v of t and sigma plus logarithm of 2. Okay? Now, again, I write the equation in the cylinder. Vtt minus n minus 2 Vt plus delta prime plus 2 minus n plus exponential of 2v is 0. Okay, this is a new equation here with this transformation. This is in 0 infinity cross Sn minus 1. What is a set of stationary solution? Is a set of omega defined on the sphere such that delta prime of omega plus 2 minus n plus omega plus exponential of 2 omega is 0 on the sphere. You have always the constant solution. Now, if n equals 3, so this is, in that case, this is delta prime of omega plus 1 minus 1 plus exponential of 2 omega. In that case, you have a whole set of non-constant solution. It's a result coming from a conformal geometry, which is a set of solutions of which are this following form. Omega is half of the logarithm of the determinant of d phi, where phi is a conformal transformation on the sphere. Now the problem in higher dimension, I don't know I don't know the result about the uniqueness. So in that case, this is not naturally unique. However, if you make in higher dimension, okay, in dimension 3, that means dimension 2 on the sphere, if you make a linearization around the constant solution, you see that there is a bifurcation. It's not surprising because you have a whole set of solutions. It is not the case in dimension n bigger than 3, but it's not because there exists no bifurcation that there exists no solution. So what we proved with Marie-Françoise in this paper in 1991, this is the theorem. You take n, it should be n equals 3, I'm sorry. If you take n, just a minute. No, it could be n equals n bigger or equal to 3. Okay. Okay. You take U to be a solution of the Hamden equation in B1 minus the origin. So you assume, since we do not have a naturally a priori estimate, I assume that the norm of x to the square exponential of u is bounded. So that proves that u is bounded from above by 2 logarithm of 1 over x plus constant. But from below, you don't know anything. Then you have the following. When t goes to 0, on r goes to 0 here, okay, either u of r plus 2 logarithm of r goes to 2 of omega plus logarithm of 2 in C2 of Sn minus 1, the specific solution of the equation. Either there exists some gamma negative, such that u of x behaves like gamma x to the 2 minus n plus constant. In that case, when gamma is negative, of course, exponential term plays no role. The equation is essentially an harmonic function. Or, in that case, u can be extended as a smooth solution. Okay, and the estimate, it's not completely obvious, but with the main tool for this type of problem, it's called the isotropy lemma, which is under the assumption of the theorem 119. You have, in some sense, an isotropy which says the following, that u of r and sigma minus u bar of r is bounded by some constant c for all r in 0, 1 times Sn minus 1. Because this is equivalent exactly to this one, because u and v differs only by the coefficient logarithm of 1 over r squared. So this is the same. So it is an isotropy. And how to prove that? This proof is used by, you use for that integral representation of the function u minus its average. U minus its average, you can write it like under this form: v star of t is exponential of minus n minus 2t times st applied to phi 0 minus integral from 0 to t of e to the minus n minus 2 over ss here, integral to 0 to infinity of e to the n minus 2 over 2t s of star applied to this function. Okay, the function f is exactly the e exponential of v minus exponential of v bar. What is st? St is a semigroup which is generated by the square root of this operator here. And now the interest is that you applied this not in whole the space, but in the space of function with 0 average. And we know that function if you have the Laplacian defined on the subspace of L2 of function with zero average, it has a first non-zero eigenvalue, which is n minus. It was a first eigenvalue, which is n minus 1. F is exactly this one. Now with this is something that I've introduced very long time ago, actually when I was preparing my thesis, and the first appeared is in 1979. Okay, this is a tool. This is a useful tool for proving kind of isotropy results. Okay, important also that in this formulation, which appears a bit ugly, that first you have in that case, the semigroup, because of this coefficient, the semigroup in this space behaves like exponential, the norm of St of phi in L2 is bounded by e to the minus n over 2 times t phi in L2. But now if you go in L infinity, you just have a constant here. So when you have this estimate, you immediately obtain the fact that all those terms are bounded. Well, yes, finally, under the assumption, the first idea was to prove that u of x plus 2 logarithm of x remains bounded near 0, or u plus is bounded. Okay, in the case we use Simon, we are just to say that there is separation. If there is no, that means that v is bigger or equal to some epsilon positive. This is a key point. This is a key point because we need that the function p to the q, or exponential of u, in that case, no, I'm sorry, I'm going to say something stupid because it's not exponential. So it's always analytic, so there is no problem in that case. So here is the result. Now, I'm sorry, here it should be the case q is, okay, there is something that I've not completely treated, which is the case where q is n over n minus 2. Well, in that case, we notice that the two coefficients here, minus 2 over q minus 1 and 2 minus s, n, they coincide. So the limit, if we want to apply the limit of r 2 over q minus 1 times u of x is always 0. So in that case, there is a phenomenon of, you have two damping effects. One is due to the nonlinear terms, minus 2 over q minus 1. The second is due to the linear terms. And this is something which is rather frequent when there is a superposition of two damping effects. Then you have an extra terms which appear. And the following result was proved by Aviles in 1987. You take u is a non-negative solution of minus Laplacian of u is u to the n over n minus 2 in b1 minus 0. Then either you have the limit of x n minus 2 times minus logarithm of x to the n minus 2 over 2 is n minus 2 the square root of 2 to the n minus 2, or u is smooth. So you see there is a kind of rigidity, and there is this additional damping effect, because in that case 2 over n minus 2 is the same as 2 over q minus 1. And what is the principle of the proof? That first you have this estimate, x n minus 2 u of x remains bounded. Then it says that you can use the energy method. The energy method will say immediately that the limit of v corresponding v is 0. That means x n minus 2 of u of x goes to 0. Okay, because omega is 0 is the only solution of the equation. In that case, the equation is just minus delta prime of omega minus omega to the n over n minus 2 is 0. This is the equation this is a possible equation. Okay. Now, by using the integral representation, well, this was not the initial proof of Aviles, but you can use the integral representation, and you show, in that case, a kind of isotropy of the solution. That means you write it in variable t as a minus logarithm of r. You have this equation here, and you have that v minus the average of v is in L infinity actually goes to 0. Well, this is almost the same because now after you have this, you can use Harnack inequality and easy manipulation of differential inequality, and then you get this result. Okay. Now I would like to say a little about the last case, which is called the conservative case. Q is n plus 2 and minus 2. And this was treated by Caffarelli, Geddes, and Spruck in Communication Applied Math in 1989, and by a technique which is called the asymptotic symmetry method, a method which is inspired from the Geddes and Spruck Nirenberg classical results. And essentially what they prove, actually, they prove a very general result. I'm going to put in a framework which is just Rn minus the origin. You assume that n is bigger or equal to 2, and q is between 1 and n plus 2 and minus 2. So there is no constraint if n equal to. You take a non-negative solution of minus delta of omega equal omega q in Rn minus 0. So first case, omega 0 is a non-removable singularity. Then u is radially symmetric with respect to this point. Second case, 0 is a removable singularity of u. Then there exists some point in Rn such that u is radially symmetric with respect to this point. Well, as soon as you know that u is radially symmetric, of course, we'll see that it is much easier to treat the asymptotics. The technique is not an easy. The question is, the idea is to use moving plane, but it's not easy to use moving plane because you don't have decay at infinity. Okay, I just consider the case of assertion 1, assertion 2 is similar. Okay, first object that by superharmonicity, I have that u of x is bigger or equal to the minimum of u of y on y equal 1. I call it beta. And the idea was how to reach some decay at infinity. Well, you make a Kelvin transform with respect to a point which is not the origin. Take a point z which is different from the origin so that you send this point to infinity, but you know exactly how it behaves. Okay, I said that I write x is y minus z divided by y minus z square, and I write the equation now, v of x is x to the 2 minus n times u of y. I have a new equation now, v has a decay, which has a decay of x to the minus n at infinity. It corresponds to the fact that this is because we are, of course, we make the Kelvin transform not from 0, but from some point different from 0. And it satisfies this equation. And the idea of Caffarelli, Geddes, and Spruck was to prove that V admits an axis of symmetry, and this is due by the reflection method. So I will not go into the proof. It's a bit long. It's extremely technical. It's very impressive. But this is the proof is to prove that you take first an axis of symmetry, and then after that, of course, you change the z into any direction. So the first idea was this one. I will not go to this point because it's uneasy. Okay, but and as a consequence, you have this symmetry. I'm going just to give you the corollary. The corollary is the following. The corollary, under the assumption of the theorem of Caffarelli, Geddes, and Spruck, theorem 22, we have the following, that if U is a non-negative solution of 3, 1 in Rn minus 0 with a non-removable singularity at 0. So when Q is, remember that is in whole space, when Q is between 1 and n over n minus 2, U cannot exist. 0 has a removable singularity, so you cannot take 0. Now, if Q is between n over n minus 2 and n plus 2 over n minus 2, then U admits a unique form. U of x is minus lambda n Q to the 1 over Q minus 1 times x to the minus 2 over Q minus 1. Now, if Q is n plus 2 over n minus 2, then you can write U of x as, okay, we know that it's going to be radial with respect to the origin. You can write it as x to the minus n minus 2 over 2 times phi of the norm of x, and phi is a periodic solution of this equation. This equation here is completely integrable. Just multiply by phi prime, and then you have the integral line of phi. Now, if it is in Rn, not in Rn minus 0, so again, if Q is between 1 and n plus 2 and minus 2, U is 0. And if Q is equal to n is n plus 2 over n minus 2, U is an explicit solution corresponding to the extremal of Sobolev inequality in R2. This is the result. So you see that the world of what happened with case Q bigger than n plus 2 and minus 2 is essentially widely open. There are many new results, but always under a supplementary assumption like the stability, which is something that I will not speak of that. Farina has worked a lot on this. Well, now I'd like to say a few words on the quasi-linear equation. I'm just going to consider two types of problem. I change this equation. I take the equation, this one. This is a generalization of Emden-Fowler equation, but you replace the Laplacian by the P-Laplace operator. And here, this is the second equation, minus divergence of grad U P minus 2 grad U. Is a generalization to the P-Laplace equation of the Lane-Emden equation. Okay? Another type of equation which are much studied is minus Laplacian of U plus epsilon U Q minus 1 U plus epsilon prime M grad U to the P is 0. Or, again, this is another type of equation. These are much more recent results, okay, but I will not speak too much on that. Okay, now we look at the equation that means the P-Emden-Fowler equation. First idea, radial solution. Radial solution, okay, computation are a bit more complicated, but you have this equation. First you have, okay, because you are in the range, okay, important that you remember that the range is here that P is less than Q plus 1. So that means this term is dominant with respect to this one, okay? Otherwise, it will fall into serine theory. So I want not to be like that. So if you look at separable solutions, then you find immediately that A is minus P over Q plus 1 minus P. I call it this expression minus beta Q. Okay. And omega satisfies some equation which is it starts to be a little complicated on the sphere. It is this one. So it is just the expression of this one with a coefficient here, which is important here, which is this important you have. So this is a diffusion operator, this is a reaction, and this is the additive term here. Now, if lambda in Q is negative or 0, which exactly means that Q is bigger than np minus 1 and n minus p, you multiply by omega, you integrate, and you obtain that there exists no non-trivial solution. Okay? So this is the same as in the case. Now, and we have with Vasquez, we prove a general removability result. Also, something which is interesting is that we have a equivalent of the Keller-Osserman estimate for a solution of the equation of the P and then Fowler equation, and the equivalent of this Emden Keller-Osserman estimate, which is due to Vasquez, says that any solution of my equation 4.1 is satisfying U of x bounded by C times x to the minus beta qp, that means q over p plus 1 minus q, q plus 1 minus p in the half ball. Okay, so this is the result of removability. Actually, it is the exact extension of Brezi's Veron result. Now, in the case where it is subcritical, we know that there exist stationary solution, that means solution on omega which are not zero, positive stationary solutions, that's a constant. And actually, by maximum principle, you can find that the only non-negative solution are for the equation here, with plus here. The only non-negative solution are the constant 0 and some omega 0, which is this expression here. And with Friedman, actually, we have the full characterization of solution with a positive solution with non-negative, with singularity. So either x to the beta, or it should be the beta pq, of course, beta pq u of x converge to omega 0, or you have a weak singularity. And if the coefficient here is 0, then you have it's a smooth solution. Smooth means that case it is C1 alpha because we don't have further regularity. And the technique is based upon Harnack inequality, which is a consequence of Keller-Osserman estimate, as it is the coefficients are due to Schrödinger, and the much use of radial explicit solution here, which are essentially the same, all have the same behavior. Okay, now in the case, now I look at the equation, the P Lane-Emden equation. The first observation is that you have the equivalent of Brezi's lemma, which is used to Biot-Veron. It was published in ARMA in 1989. You take P is between 1 and n. U is a C1 of B1 minus the origin, intersects with W1P log of B1 minus the origin. You take a function which satisfies minus divergence of grad U, P minus to grad U is in L1 log of omega. This is, of course, in the sense of distribution. And you assume that it is P, P subharmonic. Okay? Then in that case, it should be, it should then in that case, P superharmonic, I'm sorry. Then it implies that UP minus 1 is, okay, I'm going to introduce some ugly space, but they are useful, which is called the Marcinkiewicz space, which are, I will not go into the definition, but they're almost like LP, a little less. That UP minus 1 in this, it belongs to the space Mn over n minus p log. Grad U belongs to the P minus 1 belongs to the Mn over n minus p log of B1, and the equation is satisfied. So these space are also they coincide with the Lorentz space with the second coefficient infinity. Essentially, okay, this is just the integral of U over some set E is bounded by constant times the measure of E to some to the good power. This is the definition of Marcinkiewicz space. Mm-hmm. Now, okay, okay, I'm going to say in a few minutes, in the 2 minutes, just to say that the weak the case of weak singularity is treated first by Veron in 1988, and now the supercritical case is essentially open. And the first idea that in the supercritical case we do not have the a priori estimate in general, and there is a very important and beautiful result by Serin and Zhu, which says that if you look at a function u you are in this range of q. So this corresponds to the critical Sobolev exponent for in the case for the LP or for graduate to the P. You take a solution in infinity log of omega intersect with W1P log of omega in non-negative solution, assume that it satisfies this inequality. Then you have this estimate. Okay, you have this estimate. So if epsilon is 0, you have exactly an equation which is which gives you the estimate. And just to say something, that we have now in the critical case for the P Lane-Lamdan equation, it gives you exactly the estimate. But the problem is that the behavior near 0 is up to now is not easy to obtain. We have Harnack inequality with that. This is a very key point. But we cannot characterize very easily the decay because there is no energy method because of the structure. Now we can say also in the case of the P-Hamdan equation, on the P-Lane-Hamdan, what are the set of stationary solution? The set of stationary solution is this ugly object, which is not easy. Okay, and this is a very recent result of Lin and Ma, and they prove in 2024. Then the extension of the result of Gidas and Sprague, or Veron and Veron, for concerning this equation. Okay, I think I'm going to stop here because I hear some noise. Okay.
Yes. So, thank you very much. Very intensive lecture. Extremely very intensive. Thank you very much. Laurent, please send us your presentation. Really, we will study it. We will see carefully. Thank you. So, colleague, please question. We have some time for discussion. Maybe 1 to 3 minutes only. No, we have, excuse me, we have some 12 minutes till the next lecture. So we have time for discussion. Please, who would like to ask to take part in the discussion? Colleague, please ask a question. Whether have you something in written form or not? I see where it is. No, I don't see any question in written form.
But you will have my slides, so if the people want to see, they can see.
Yeah. Well, extremely intensive because it's very difficult to follow. Really, it's necessary very carefully. But you gave all this history of this story. It was really very intensive. I didn't see such a complete some survey of this subject. Really, thank you very much, dearly. Colleague, excuse me. Excuse me. Please, question. Have you some question? No, maybe all are very impressive, really. So we will study this presentation. Maybe some question will appear. So once more, Professor Veron, thank you very much. Thank you very much.
It was a pleasure to be.
You finished your course, and it was very nice, very useful, very useful course.
It's always a pleasure to cooperate with this university.
Yes, I guess it will encourage such cooperation.
Continuation of this cooperation.
Yes. So I have some propositions, some questions. We will discuss really.